Hi everyone, this is the second part of our YOLO V2 to V5 video, in which we'll get into YOLO V4. In the previous part of this video, we looked at YOLO V2 and V3, and we are going to cover V5 in the next one. Up till now, all the YOLO versions that we have gone through were by the same authors, but post YOLO V3, changes which were packaged together as YOLO V4, YOLO V5, and so on were made by different folks. After the release of YOLO v3, there were quite a few object detection models which ended up getting more accurate detection compared to YOLO family of models, while being faster. The authors of YOLO v4 bridged this gap and pushed the performance of YOLO family of models further to achieve state-of-the-art results at the time of publication. The authors used features and techniques from different research works which were focused on improving CNN accuracy. Some of these can be universally applied to most models, tasks, or datasets. They aggregate all such features as well as techniques specific to object detection tasks and test the influence of all of these on detectors' performance to come up with the most optimal model in terms of speed as well as accuracy. By the time of YOLO v4, most object detectors used in architecture that could be divided into three parts: a backbone, which is often pre-trained on a large classification dataset to act as a strong feature extractor for the detection task; neck, which is tasked with refining features extracted from backbone and commonly also aggregates the features extracted at various stages of backbone. The main purpose of this aggregation is to enhance semantic and localization information across all scales. Head is the last part that takes in the features from neck and finally predicts the bounding boxes and class information. If we go back to the YOLO v3 architecture that we saw in the last video, we can apply the same categorization to that as well. Here the backbone is Darknet53, which were these layers. Neck was an FPN, which used top-down pathway to aggregate features from different stages of darknet. And finally head were these last convolutional layers which predicted localization, objectness, and classification scores for all prior boxes at all grid cell locations. And the head was used to make predictions at 3 scales. For YOLO v4, after lots of experiments, the authors finalized with CSPDarknet53 as their backbone, neck comprising of Spatial Pyramid Pooling and Path Aggregation Network, and head is just same as YOLO v3. The authors also experimented with a whole bunch of features and techniques to reach the combination of features that ends up with the best detector, which they group into bag of freebies and bag of specials. In this video, we'll first go through each of these features in detail and then look at different parts of YOLO v4 architecture, understanding CSP Darknet, Path Aggregation Network, and all the other aspects of it. So let's start with YOLO v4. And the first thing that we'll look at is what exactly does this bag of freebies and bag of special mean. The authors define bag of freebies as the collection of techniques or methods that do not increase the inference cost of detector, but end up giving an accuracy boost. However, these may impact the training cost. Examples of these would be data augmentation. Obviously, it would make the detector robust, but it would have zero impact on inference cost. Similarly, using a better loss for either backbone or detection fine-tuning stage. Again, no impact to inference cost, but can lead to higher accuracy. The other set, which is bag of specials, refers to methods which increase the inference time marginally but lead to significant improvement in accuracy. Examples of these could be using attention module, adding which will increase the inference cost but also might improve accuracy. Another one would be feature aggregation in neck, which YOLO v3 does using FPN. It definitely adds to the inference cost, but again gives us a more accurate detector. So the key distinction between both of them is how they impact inference cost. Let's start with bag of freebies for backbone. These would be the strategies used during ImageNet pre-training stage to boost the classification accuracy and end up with a stronger feature extractor. So we'll go through the bag of freebies for backbone that authors use in YOLOv4. The first is Cutmix, which is a data augmentation method. Usually, during classification training, our data points will have ground truth class label as 1 and rest all classes label will be 0. But in Cutmix, we mix patches of two images by overlaying a patch of one image onto another. Implementation of Cutmix is very simple. We decide what would be our overlaid region's width and height and the starting point of our overlaid region. Then for pixels belonging to that region, we simply overlay the pixels of a different image onto this one. The ground truth label in Cutmix is now mixed proportionally according to the area of patches. Here, this is the overlaid area from the image belonging to cat class, and this is the dog area, which means our ground truth label during training with Cutmix will be this, as about 40% of the image area belongs to cat class and rest to dog class. Because this model is trained on a mixture of images, the classifier is forced to attend on non-discriminative parts of objects like legs of dog rather than face, and hence ends up being more generalizable. Furthermore, it gives the model the ability to identify objects from their partial views, which will definitely benefit in cases where the object itself is occluded. The authors of Cutmix showed that with this augmentation strategy, we not only end up with a better classifier, where we get close to 2% improvement on classification accuracy, but when this classifier network is used as a pre-trained model for detection fine-tuning stage, we end up with performance gains in detection as well. Next freebie is Mosaic, again a data augmentation strategy, and also very similar to Cutmix. Here we are basically combining 4 images and feed a combination of 4 images as the final image to the model during training. There's also a version that combines 9 images, but let's work with 4 for now. The way this is implemented for classification training is that you have your image size that the classifier network takes as input, and we pick a random point on it. This divides the image into 4 patch areas, each of which correspond to patch areas that will be taken from these 4 different images. And ultimately these patches, which belong to different images, will be combined to make our input to the model. For labels, again, we use the area of patches relative to image area to decide the final label. For example, let's say we have roughly 10% of this image belonging to the first one, and then 20, 30 and 40% belonging to the other 3 images. So the label for this image will be 0.1 times the label of first one, plus 0.2 times that of second, plus 0.3 and 0.4 times the label of third and fourth image. We are also going to be using Mosaic during detection training, but for detection the implementation is slightly different. For a 2x2 Mosaic, we still combine 4 images, but now we start with a canvas of 2 times the width and height of image that our detection network takes as input. We pick a center point on this canvas and place the grid of 4 images at that point. Obviously, when the point we picked will not be at the center of the canvas, some parts of the image will be excluded. Then we crop out the image of desired width and height from this canvas. During detection as well as classification training, the goal of Mosaic is same as Cutmix, to teach the model to recognize objects in spite of occlusion, as well as enable the model to learn to recognize and detect objects in different contexts. Moving to Dropblock. So this is a regularization technique, and usually in our neural network, we would use dropout as the regularization technique. So let's first understand why was Dropblock even introduced. In images and feature maps of convolution network taking images as input, spatially adjacent features exhibit strong correlation. So applying standard dropout will not really remove semantic information to act as a good regularization technique. Like here, even though we have used dropout, because the neighboring activations contain closely related information, most of the semantic information regarding the dog will still be present, or at least can be inferred from spatial neighbors. Hence, a common practice is to have spatial dropout in convolution layers, where we zero out the entire feature map itself. But the authors of Dropblock use a completely different strategy. Instead of dropping out random activations in the feature map or dropping out entire feature maps itself, they drop continuous regions. Removing continuous activations has the potential to remove semantic information from the image, and thereby enforcing the non-dropped out units to learn features that enable the model to discriminate the object. Like here, removing one continuous block will remove all semantic information corresponding to the head of the dog. So how do we remove these continuous regions? We'll go through all the steps and apply Dropblock on a sample feature map to understand this. Given a feature map, we first create a mask which has 1 in cells which we want to drop off and zeros which we want to keep. The reason we have 1 in cells that we want to drop off rather than zeros is because we'll be performing some operations on it for which this kind of initialization makes more sense. It'll soon be clear why. Then we flip this mask, and this flipped mask, which now has 0 in regions where we want to drop the activations, this will be multiplied with the feature map. Let's say we have this 5x5 feature map. We start by sampling a 3x3 mask according to some probability. So say the probability that we used to sample this mask was 0.1. Then maybe only this cell will be 1 and rest all will be zeros. In implementation, to get this mask, we would sample 9 numbers according to Bernoulli distribution, parameterized by our dropout probability. Now for a 5x5 feature map, we actually sampled only a 3x3 mask. Why we did that will become clear a bit later. For now, let's go with this 3x3 mask and move forward with the next steps of Dropblock. We pad this mask with zeros to match the shape of our feature map. So after zero padding, our mask is also 5x5. Now to get continuous regions dropped out, we first run max pooling operation on this mask with a padding of 1. The max pooling kernel size as well as padding will be decided by a block size parameter, which basically conveys the strength of regularization that we need to use. Larger block size means we would end up removing more semantic information. Let's assume our block size is 3. So the max pooling will be a 3x3 kernel which would continue moving across the image and expanding the mask. For the remaining part of the output, let's only worry about locations where the pool operation will have a non-zero value. So this is the last location which will have non-zero pooled output with this mask as input. Going back to the block size parameter, our block size, which also decided our kernel, was 3x3. So the single non-zero mask unit ended up being expanded to 9 other locations. Had we used a 4x4 block size, then we would get an output with 16 positions with value 1 and remaining all zeros. And if our block size was 2, then we would only have 4 positions with 1. So this is why a larger block size leads to more semantic information being removed and hence stronger regularization. Also now it makes more sense why we started with a mask with 1 where we want to drop activations. It's because we would be using the max pooling operation to expand the masked regions. But obviously ultimately we need the inverse. Regions that we are going to drop out should be 0 in the mask and remaining all ones, which is why now we flip this output mask and finally multiply the 5x5 feature map with this mask. This is how we drop continuous regions of the feature map. This entire operation happens for all channels of the feature map, with each channel having its own mask. But the authors of Dropblock also tried a setting where the mask was shared across channels. However, it did not perform as well as the former case. To make sure that we understand everything about Dropblock, there are a couple of things that we need to address. First, even though our feature map was 5x5, we sampled a mask of 3x3 and then zero padded it to match the size of 5x5. Why did we do that? Well, the reason is, in Dropblock, our initial mask is such that every sampled entry, that is 1, can be completely expanded in all directions while being fully contained within the feature map. Let's understand what this means. Say instead of 3x3, we started with a 5x5 mask and our block size was 3, which means each sampled entry, that is going to be 1, will be expanded to 9 locations. Now, if this corner region of the mask is sampled to be dropped off, then we cannot expand this entry in all directions with max pooling. We can't expand in top or left direction without going outside the feature map, creating a distinction between entries that are in the corner versus those that are somewhere in the center, which can indeed be expanded in all directions. In fact, for a 5x5 feature map and block size 3, only cells contained within this region can be expanded in all directions. Which is why we started with a sampled mask of 3x3 and then padded it with zeros to make it 5x5. Because now, even if the corner sampled entries end up being 1, they can be expanded and still be within the 5x5 feature map. The second aspect that we need to understand is parameters in Dropblock. There are two parameters. One is block size, which we saw decides that for each sampled entry, that is 1, how much semantic information gets removed from the feature map. With a block size of 3, every sampled entry, that is 1, will be expanded to a 3x3 block of all ones, whereas with a block size of 5, it will be expanded to a 5x5 block of all ones. So a higher block size means more information being dropped out, which means greater regularization. Again, just to reiterate, this is prior to flipping. So when I say entry being 1, it means it will be dropped out. The other parameter of Dropblock is gamma, which controls sampling in the original mask. In our case, 3x3 mask. It will dictate how many entries in this mask will be 1. Now assume that we want to drop 50% of regions in the final feature map. To do this, we can't really sample a mask such that 50% of cells within it are 1. Why? Because as a result of max pooling, each of these entries with 1 will be expanded to block size square times. So even though you began with a mask in which 50% of cells were 1, post max pooling, we'll have more than 50% of cells that are now 1. Which is why, rather than creating initial sample mask with the dropout probability, we divide with block size square term. Again, because each sampled 1 will be expanded to block size square once, which will all become zeros after flipping. But we are not done with gamma yet. Since we want the mask to be contained inside the feature map even after expansion, we don't start with a mask equal to feature map size, like 5x5 in our example. Rather, we start with a mask smaller than that. In our example case, we had 3x3 mask. This is why the authors further scale the gamma for sampling by this term, so that after zero padding and expansion via max pooling, we have roughly dropped out same fraction of activations as the dropout probability. The implementation of Dropblock pretty much repeats the same set of steps that we covered. So let's look at all of them in action. We start with computing the gamma for our sampling distribution. The formulation is similar to what we talked about. We create a mask of smaller size compared to feature map and fill the mask values according to the gamma computed prior. We zero pad this mask to expand it to be of the same size as the feature map, and then apply max pooling with padding to ensure that the output of max pooling has the same shape as feature map. Post that, we flip the mask and multiply the feature map with this flipped mask. And also, like normal dropout, scale the non-dropped out activations. That covers Dropblock implementation. And in terms of performance, the authors of Dropblock show that this regularization strategy leads to a boost in classification accuracy. Now let's move to the final freebie for Backbone, which is label smoothing. This is a change in ground truth labels used for classification training. It's a common idea that is meant to tackle overfitting of network and act as a regularizer. Our classification ground truth labels look like this, and commonly we use cross entropy to train our classifier. Here Q is the target label, which is 1 hot, with the ground truth class being of label 1 and remaining 0. Pi is the probability prediction by the classifier for the ith class. Usually the network predicts logits, and we have a softmax function on top of logits to get class probability scores Pi. The classification loss will try to have the model generate probabilities that are closer and closer to this target distribution throughout the course of training. But the softmax function can only approach this target one-hot distribution if the logits of the ground truth class are significantly greater than the logits predicted by the model for all the other classes. Now, while it can approach this one-hot distribution, it will never reach it. Because even if you have two classes, and for one your logit prediction is 10, whereas for the other it's 0.1, it still will not be exactly the target distribution. What this means is that because we are continuously forcing the network to be closer and closer to this one-hot distribution, it will encourage the model to be too confident in its predictions in an attempt to match the one-hot distribution. The network will keep on trying to produce larger and larger values for the correct class logits by using larger weight values and overfit more and more to these training data points. To avoid this, we instead reduce the ground truth class label for the correct class by a small value and increase the ground truth labels of incorrect class by a small value. This constrains the largest logit to not become much greater than the remaining logits, acting as a regularization technique. In implementation, we do this by multiplying the class label with 1 minus ls and adding ls by k, where ls is label smoothing parameter, typically equal to 0.1, and k is number of classes. So when the number of classes is 10 and ls is 0.1, we end up with the ground truth label for the correct class as 0.91 instead of 1, and for incorrect classes as 0.01 instead of 0. With label smoothing done, we have now covered all techniques that are in the bag of freebies for Backbone section in YOLOv4. Next, we are going to look at bag of specials for Backbone. The goal of using them would also be to get a boost in accuracy, but like we had seen earlier, these techniques or features would also lead to an increase in inference time. We'll be looking at three features here: Mish activation, cross-stage partial connections, and multi-input weighted residual connections. Let's start with Mish. This involves replacing the leaky ReLU activations with Mish activation. If you remember, for all the convolution layers in backbone of YOLOv3, we had used leaky ReLU. So now we'll simply replace that with Mish activation, which has this formulation, where soft plus is defined as log of 1 plus e raised to the power x. When x is positive, Mish is very similar to ReLU, at least for large values. But when x is negative, rather than 0 leading to dying ReLU problem, we get a smooth transition with small negative values. Furthermore, the Mish function is non-monotonic and hence potentially captures richer representation than ReLU. When the authors of Mish compared it to different activations, it ended up performing significantly better than a lot of other activations. By the way, the reason Mish is in bag of specials and not bag of freebies is because it leads to an increase in the time taken to do forward as well as backward pass through the network. Now moving to cross-stage partial connections, which was introduced with this paper. In this paper, the authors used DenseNet as a backbone to demonstrate the benefits of cross-stage partial connections in DenseNet blocks, and then show how it can be extended to other kinds of blocks. Rather than DenseNet block, I'll use residual block that we had seen in YOLOv4 as an example to explain CSP connections, as this is what we are going to be working with in YOLOv4. And here we have just used two consecutive conv and residual connection as an example. The input goes through 1 cross 1 to reduce channels, then 3 cross 3 convolutions followed by a residual connection. In YOLOv4, at different stages, this was repeated different number of times. But here let's work with an instance where it's just repeated 2 times. In cross-stage partial connections, the input is first split into 2 parts. This split happens along channel dimension. One part with half the channels goes through the residual block as before, whereas the other part does not go through any modification and it's straight away concatenated with the output of residual blocks. This concatenated feature becomes the output of this entire CSP residual module. We also have transition functions, which is simply 1 cross 1 convolution layer in implementation. This 1 cross 1 is applied prior to concatenation on the output of residual blocks. The concatenated feature again goes through a 1 cross 1 convolution transition function and becomes the output of CSP residual module. So why do this cross-stage partial connections? The first benefit that you can see is that because we split and pass only one part of the original input through the residual blocks, we have effectively reduced the computational cost of residual blocks because of this split and merge strategy. Secondly, because of these different gradient paths, our network will now be able to achieve a richer gradient combination than before. In the paper, the authors used DenseNet as an example to further show that CSP connections with transition layers prevent the network from learning duplicate gradient information as well. Here I have just gone through a quick overview of CSP connections without going through DenseNet because it's really not needed for this video. But do read the paper if you want to get a much better understanding of CSP, especially in context of benefits that CSP DenseNet block has over DenseNet block. For this video, all that we need to understand is how Darknet53 is transformed to CSPDarknet53 using what we know about cross-stage partial connections. This was our Darknet53 backbone that we had looked at in the last video. And let's just see how this entire block will be modified as a result of moving from Darknet53 to CSPDarknet. This same modification will exist for all other blocks. Earlier, the input of this 8 residual blocks was the output of a downsampling layer, and the output of these blocks was again passed to another downsampling layer. Now in CSPDarknet, the entire block will take the downsampling output and first split it into 2 paths. In implementation, we do this via 1 cross 1 convolution layers. If the downsampling output has 128 channels, then each of these 1 cross 1 layers will have 64 filters to produce 2 parts containing 64 channels each. One of these parts will then go through the 8 residual blocks. After all the residual blocks, we have a transition layer, which is just 1 cross 1 convolution layer. The output of this layer is concatenated with the other part channel-wise. Then we again have a transition 1 cross 1 layer, and finally the output of this layer is fed to the next downsampling layer. CSPDarknet53, which is going to be our backbone for YOLOv4, is just Darknet53 with the original blocks replaced with these CSP blocks. The next and last bag of special for backbone is multi-input weighted residual connections. This is from EfficientDet paper, and it specifically caters to the scenario when we are fusing features of different resolutions together. The neck of EfficientDet does something different for cross-scale connections. And by cross-scale connections, I mean connections that are meant to fuse features of different scales together. Instead of resizing inputs to the same spatial resolution and then simply combining them, like we had seen in FPN of YOLOv4, the authors of Efficient Det have the network learn weights to decide the importance of each individual feature involved in fusion. These learnable weight parameters can either be per feature, so one scalar value learned for each input, or per channel. For combining the input using the learned weights, the authors tried three different fusion variations. Unbounded fusion, where we don't have any normalization of weights. Softmax fusion, where we use softmax to normalize the learned weights from 0 to 1. And another variant of normalization, which does not require us to do softmax. Here, to ensure that all the weights are non-negative, the authors of Efficient Det add a ReLU as well after each WI. The authors of YOLOv4 also experiment with the same neck as Efficient Det, and when they do so, they also use these learnable weights for feature fusion. Now we are done with all the features that the authors use for backbone training. Next, we are going to get into bag of freebies for detector, which would be used during detection fine-tuning stage. And again, these would have no impact to inference cost. Specifically, we'll be looking at the following list of freebies. So let's start with the first one, that is cross mini-batch normalization. Batch norm is a widely used technique that improves convergence of deep neural networks, where we normalize activations for a layer. But for normalizing each activation, how do we pick the distribution statistics? That is mean and variance of the distribution of each of those activations. Ideally, given current parameters of the model, this would be the distribution of each activation by taking into account the entire training dataset. But that's really not possible. So rather than using statistics from the entire training set, we use current batch to give us an estimate of the mean and variance of each activation and normalize accordingly. Additionally, we also have learnable scale and shift parameters so that the transformation can also represent identity transform if the network believes that ignoring the normalization that we inserted is the optimal thing to do. To understand cross-mini batch normalization, we actually first need to understand cross-iteration batch norm. The authors of cross-iteration batch normalization reason that using batch statistics as an estimation works great if we have larger batch sizes. But as we keep on decreasing the batch size of network, the accuracy in this estimate also keeps on decreasing. This becomes a bit challenging for tasks like object detection, where we want to feed the network with large size input images to be able to detect objects of even smaller sizes, which means to do that we have to reduce batch size because of memory constraints. But then because of smaller batch size, our batch statistics start becoming noisy estimates. To alleviate this problem, they introduce cross-iteration batch norm, where they utilize examples from recent batches or iterations to make the estimates from smaller batch sizes more reliable. So let's say we decide to utilize statistics of last 4 batches to make our current batch statistic less noisy. And suppose these are the means for these batches for activations at a particular layer L. Unfortunately, we can't simply aggregate the past 4 batch statistic to make our estimate less noisy. Why? Because the activation values aren't comparable across batches, as the weights of network itself is different across batches. To fix this, the authors of cross-iteration batch norm compensate for network weight change, using the fact that weight changes in the network is smooth and few other approximations. They approximate the statistic of activations for a particular layer corresponding to current weights but in a past iteration in this manner. The paper has more details on how they arrive at this formulation, but once you have these compensated statistics, we can now aggregate to make our estimate less noisy and normalize current batch using these less noisy statistics. In YOLOv4, the authors use cross mini batch normalization, which is just a modified version of cross iteration batch norm. where rather than aggregating statistics across batches, we aggregate statistics across mini batches within a single batch. To understand what's exactly changing from batch norm to cross-iteration batch norm and then to cross-mini batch norm, let's start with the overview of steps within batch norm. Say we have these 4 batches and each batch has 8 examples. In batch normalization, for each batch, we would first compute mean and variance for the current batch. So from the activations of these 8 examples present in the batch. Then normalize features according to this statistic. And finally, during backprop, update the weights of the network for each batch, as well as update learnable scale and shift parameters of batch norm. In cross iteration, we saw how we aggregate statistics of past k batches, so the steps will be slightly different. We first compute statistics from the current batch, then aggregate the statistics from the current and last k-1 batches, but compensating for the network weight changes for the previous batches. Normalize features using this aggregate statistic, and then update weights of the network in backprop, and also update learnable scale and shift of batch norm. For cross mini batch normalization, we'll aggregate statistics within mini batches of a single batch. So assume our mini batches are of 2 examples, and batch size is still 8. For the first mini batch, we compute mean and variance from activations of these 2 examples, normalize features, but now we won't update the weights. Rather, we'll only accumulate gradients as of now. And once all the mini batches have been dealt with, then we'll actually update the weights for the entire batch. For the next mini batch, we do the same set of steps of computing statistics and accumulating gradients. But for normalizing, we aggregate the statistics of this and the previous mini batch and normalize using this aggregated statistics. One aspect that's different from cross iteration is that now we don't need to compensate for network weight change, because all the statistics that are aggregated are being computed with the same network weights. The same steps are repeated for the third mini batch, except now you are aggregating statistics from all 3 mini batches. For the last mini batch, we again do the same steps, but aggregating statistics from all 4 mini batches. For this last mini batch, we also additionally update the weights of network using all the accumulated gradients, as well as update scale and shift of batch norm. There is a small implementation detail left to cover here, which is how the aggregation happens. For this, the authors define this alpha underscore CBN coefficient, which is 1 by mini batch index plus 1. So alpha will be 1 for the first mini batch, 0.5 for second, 0.33 for third, and 0.25 for the last mini batch in this example. Then to aggregate the mean statistic, the authors define aggregated mean as alpha times mean of current mini batch plus 1 minus alpha times aggregated statistic from past all mini batches, which means the aggregated mean for the first mini batch would just be the mini batch statistic. Aggregated mean for the second mini batch would be half of second mini batch statistic plus 1 minus alpha times the current aggregated mean, and so on. So this is how cross mini batch normalization works. In this video, I haven't done a very good job at explaining all details of cross mini batch norm because there are just too many. But if you want to understand it for yourself, I would suggest to first read cross iteration batch norm paper. Here I've used mean as an example throughout, but to understand how the variance is aggregated, you would need to go through that paper. Once you have understood cross iteration batch norm, for cross mini batch normalization, you can just take a look at the implementation in YOLOv4 repo, specifically within this method. That should give you a much clearer picture of cross mini batch normalization, much better than this very high level overview that I gave. Okay, after this very long segment on cross mini batch norm, let's go back to our next important bag of freebie, which is complete IOU loss. The localization loss that we have been using up till now is MSC, between box coordinates. Now imagine this ground truth box and this red predicted box. For the illustration, assume we are using the x1, y1 and x2, y2 coordinate system for defining a box rather than xy, wh. These are the x1, y1 and x2, y2 points for the boxes, the distance between which the MSE loss is trying to minimize. Let's say we have fixed the top left corner of both these boxes, and now we are drawing a circle with the radius same as the current distance between the x2, y2 points of both these boxes. The center of this circle is on the x2, y2 corner of the ground truth. With the ground truth box fixed, if we change the x2, y2 corner of this predicted box to any point on this circle, MSE loss would still be the same. As x1, y1 points are exactly same as before for both the boxes, and distance between x2, y2 will still be the same as we have moved along the circle. This means that for this prediction box, the MSE loss would be exactly same as the first case. But obviously this second predicted box is much better with larger overlap. Furthermore, the MSE loss is also not scale invariant. If you take these boxes and just reduce them in scale, distance between the coordinates will also reduce and thereby reducing MSE loss. However, in terms of overlap, they still have the same IOU with each other. These problems indicate that MSE loss might not be the most optimal loss choice if our goal is to train the network to predict boxes which have higher overlap with ground truth. So how can we do better? Well, one thing obvious that comes to mind is that if you want the network to predict boxes with higher IOU with the ground truth, so just use that as loss. We would have to use 1 minus IOU for this, as we want the loss to decrease as IOU increases. But there is a problem. While this formulation enables us to achieve our goal of higher overlap, having less loss value, however, cases when there is no overlap, they all end up being treated as equal. So if your boxes are these or these, the IOU loss will still be the same. But you would want to let the network know that the right case is better, because after all, while the overlap is still 0, at least the boxes are closer. To fix this, the authors of this paper introduced a new loss called Generalized IOU loss, which adds a penalty term to IOU loss to handle cases when there is no overlap. This penalty term is smaller if the boxes are closer and larger when the boxes are farther, making the loss also larger for such cases. Let's understand this penalty term closely. The generalized IOU loss can be applied to different types of geometric shapes, but let's limit our discussion to 2D boxes. The denominator here refers to the area of the smallest box enclosing both the boxes, which means for both these examples, it would be this area shaded in green. The numerator is this area excluding the union of both the boxes. For the left scenario, the sum of areas of blue region is the union, which means the numerator is this white region. Similarly, for the right scenario, these are the box areas, and excluding union of these, we get this white region. So the penalty term represents a normalized measure of empty area between the two boxes, and closer the boxes are, lower this empty area is. The authors of Generalized IOU loss show that using this loss results in a detector that has better performance than not only MSE but also IOU loss. Now we are going to move from Generalized IOU loss to Complete IOU loss, which is actually the loss used in YOLOv4 and was introduced in this paper. Let's first understand the motivation of trying anything different than Generalized IOU loss. The authors of Complete IOU loss found in their experiments that given an anchor box, predicted box, and ground truth box, Generalized IOU loss usually leads to first increasing the size of predicted box so that it has some overlap with the target ground truth, and then once we have non-zero overlap, the IOU term kicks in and ensures the predicted box matches the ground truth. Had we instead directly reduced the distance between the two boxes, we would achieve faster convergence. Furthermore, Generalized IOU loss is also not the optimal loss for certain cases. For instance, take this scenario of the predicted box enclosed within the ground truth box. Since all three cases have the same union and intersection area, IOU loss will be of the same value, but in terms of prediction, you would prefer the last prediction, where at least the location of center is perfect, and only the size of box could be better. What about generalized IOU loss for these cases? Well, for these cases, generalized IOU loss actually degrades to IOU loss itself. Since for all three cases, the penalty term is of the same value, which is 0. Since the area of smallest box enclosing both is the ground truth box area, and the union is also the ground truth box area, making the numerator of the penalty term to be 0. The authors of complete IOU loss introduce a different penalty term to handle this, as well as the original non-overlapping case that generalized IOU loss was introduced to handle. The numerator of this penalty term is the square of distance between the centers of two boxes. The denominator is c square, where c is the diagonal length of the smallest box enclosing both boxes. Since this penalty term captures the distance between centers, we not only cover the non-overlapping cases as before, but we also capture the case when one box encloses the other, which the generalized IOU loss did not. But this is still not the complete IOU loss. This is called distance IOU loss. To see why we even need complete IOU loss, imagine the case when both the boxes, predicted and target, have the exact same center, but their aspect ratios are different. Now these two cases actually have the same IOU, and their penalty term from distance IOU loss is 0, since their centers are same. So for both cases, distance IOU loss is same. But we would prefer the right one, because the prediction box, while having the same IOU as left one, has also the same aspect ratio as the target. This is why the authors add another penalty term which specifically caters to mismatch of aspect ratios. The term alpha here is just a trade-off parameter which the authors define as this. In terms of performance, the authors show that distance IOU loss gets better performance than generalized IOU loss, and even the convergence is faster. With complete IOU loss, we get even better performance than distance IOU loss. So with complete IOU loss done, now we'll be moving to the next bag of freebie for detector, which is self-adversarial training. Adversarial training is to make the model more robust, and here is what we do in it. Assume this is an image from your detection dataset with this ground truth box and label. During adversarial training, the network goes through two forward-backward stages. In the first stage, we don't change the weights of the network and compute the loss according to the label that there are no objects in the image. So you're computing the loss based on the label that this image has no dog. Then using the gradients of the loss, we alter the image. Now that this image is altered in a manner which makes the network with the current weights believe that there is no dog in it, in the second stage, we pass this altered image. But this time, we use the original labels to compute loss, which means that using the gradients of this stage 2 loss, the network weights are updated to ensure that the network predicts the right label even for this altered image. So in stage 1, we produce the image that is going to confuse the model, and then train the model on that altered image in stage 2 to make it more robust. Next pack of freebie is eliminating grid sensitivity. Going back to YOLOv4, if you remember, we were predicting XY location of the center of box as offsets from the top left corner of the grid cell corresponding to the box. And during inference, our box center location becomes the grid cell location plus offset prediction. For predicting the offsets, we used sigmoid to bound the prediction from 0 to 1, thereby ensuring that the center is always within the grid cell. Now think about what happens if our ground truth box's center is here. or even here. Basically, anytime the box prediction is at the boundary, we need the x prediction to be Cx or Cx plus 1, or y prediction to be Cy or Cy plus 1. So we need the output after sigmoid to be either 0 or 1. But in order to produce 0 or 1 as the output of sigmoid, the network would now have to predict a large absolute value. Like take the case that after sigmoid, we need the output to be 0. Even if the network predicts a value of tx to be minus 4, the sigmoid output will be small, but it will still not be 0. And we can keep going to larger negative numbers. Again, closer to 0, but not 0. For it to be really 0, the network ultimately needs to predict a very large negative value prior to sigmoid. And similarly, for the sigmoid output to be 1, the network needs to predict really large positive value prior to sigmoid. This makes it tough for the network to predict boxes which have center on the boundary. To reduce this effect of grid, the authors of YOLOv4 changed this location offset prediction from adding output of sigmoid to Cx or Cy to this. So we multiply the sigmoid output by a scaling factor alpha and simultaneously subtract 0.5 times alpha minus 1. Essentially, this whole part changes the range of values that are added to Cx or Cy. Earlier, we were simply adding the sigmoid output, which means the range of values being added were 0 to 1. This is still the scenario with alpha equals 1, as it reduces to the older center location offset conversion. But when alpha equals say 1.25, our range of values that are added to Cx or Cy is from minus 0.125 to 1.125. But how did this solve our problem? We still have sigmoid, which won't give us 0 or 1. At least not exactly. So yes, that's true. But because we have multiplied the sigmoid output with alpha, which is greater than 1, we don't need sigmoid output to be 0 or 1. Even if it's 0.1 or 0.9, we will be able to get the coordinate value of Cx plus 0 and Cx plus 1. To be very specific, for alpha equals 1.25, even if the network now predicts a value of Tx to be 2.197 in absolute value, these are the values that we get after sigmoid, which makes the values being added to Cx, as in the value of everything within this red box, to be equal to 0 or 1. This enables us to be in a better position to predict the box center locations even at grid boundaries, for which earlier we needed very large magnitude predictions of Tx. If we use alpha equals 1.5 or 2, we further increase the range of output values and require lesser absolute magnitude of Tx for boundary cases. For YOLOv4, the authors use different values of alpha for different scale predictions, but they are all greater than 1 to reduce this effect of grid. In the repo, you can find extensive discussion on grid sensitivity in this issue. So do check it out to understand this in more depth. Let's proceed further in our bag of freebies list to cover the last one, which is genetic algorithm. In the paper, the authors of YOLOv4 mention that they use genetic algorithm to find the optimal hyperparameters. Here is what happens in it. We start with initial hyperparameter values. So these would be learning rate, augmentation probabilities, and so on. Then we evolve these hyperparameter choices over k generations, typically k being somewhere in the range of 100 to 300. But what exactly does evolve mean? So we first train the model using the current hyperparameter choices, generate fitness score for the current hyperparameters. This score basically reflects how good the current choice is, and we consider multiple metrics like precision, recall, MAP for deciding fitness. We define weight values for each of these metrics, and then the fitness score is just weighted sum of the values corresponding to these metrics. Once we have this score computed for past training iterations, then we randomly pick one of the top performing hyperparameter choices based on this fitness score. We can either pick a random choice from say top n hyperparameter settings or weighted combination of top n settings, where the fitness scores are used to decide the weights. Now this selected hyperparameter setting is mutated. By mutation, we simply mean the setting is modified a bit. This mutation happens with a probability and variance value. The probability decides how often that hyperparameter will be modified, and the variance decides how much that modification will be. Then as we go through this process of training the model, selecting best choices, and mutating the best ones, over time, only those mutations which benefit the fitness score persist, because only those will be selected as top performing choices and further modified. Ultimately, after all k generations, we have our optimal hyperparameter setting as a result of this evolution. Do note that this is a very expensive process, as you're basically going to train your model k times. You could, however, decide the fitness score based on only 10% of the actual number of epochs to save some time. I couldn't find the code in Darknet YOLOv4 repo, so if you really want to understand the exact mechanism of this evolution, you can use the code in Ultralytics repo to get a sense of what's happening during the evolution of hyperparameters and how exactly are they mutated. That finishes our bag of freebies for detector. Let's now move to bag of specials for detector. And in this list, we'll cover Spatial Pyramid Pooling or SPP, Spatial Attention Module, Path Aggregation Network, and DIOU NMS. Let's start with Spatial Pyramid Pooling. The main motivation of using SPP is to increase the receptive field of backbone features. Within the SPP block, we take the backbone feature and apply max pooling with relatively large kernel sizes. Specifically, we have a 5x5 max pooling, 9x9, and 13x13. The original input to the SPP block is then concatenated with all the three max pooling outputs along the channel dimension. This concatenated feature is the output of SPP block, which allows the model to capture relevant context information to make better detection predictions. In the architecture, SPP block is present right after the last layers of backbone. From SPP, we now move to SAM. Spatial Attention Module is taken from this Convolutional Block Attention Module paper. The authors of this paper use both channel and spatial attention. Let's just take a peek and see how both these modules work, and then we'll get to what happens in YOLOv4. Channel attention focuses on asking the question of what, as in out of all the features captured through the channels in the feature map, what are the more meaningful features given an input image. For the channel attention block, the authors first aggregate spatial information using both average and max pooling. The output of both these aggregations are C cross 1 cross 1. These are then forwarded to a shared MLP. The outputs of MLP for both aggregations are then added and after sigmoid multiplied with input to get a C cross H cross W output. For spatial attention block, the goal is to identify where the informative part is. For this, the authors first apply max pooling and average pooling along the channel axis, and then concatenate both these together to get a 2 cross H cross W output. Then using a 7 cross 7 convolution layer, we generate our spatial attention map of shape 1 cross H cross W, which after sigmoid is multiplied with input to get a C cross H cross W output. The authors of YOLOv4, rather than having channel and spatial attention module, have a SAM block which just applies pointwise attention. Specifically, the input goes through a 1 cross 1 convolution layer with same number of filters as their channels in the input. This convolution layer has a sigmoid activation, and its output is then multiplied with the original input. In YOLOv4, in configurations where SAM block is used, we have it just before the prediction convolution layers for each of the scale predictions. From SAM, we now move to the last bag of special in terms of architecture changes, which is Path Aggregation Network. Remember in YOLO v3, for the NEC, we had a FPN-like structure, which was meant to combine low resolution but semantically strong features with higher resolution but semantically weak features. This allowed us to use the higher resolution features to make predictions for small-scale boxes, as they were fused with higher semantic knowledge from the top-down pathway. In YOLO v3, for fusing the features of different scales, we first took the lower resolution feature and upsampled it, then concatenated it with the higher resolution feature map that we took from an earlier stage of the network. The concatenated feature map went through a bunch of convolution layers before our prediction layers for each scale. The authors of Path Aggregation Network paper found that while this top-down pathway ensures that higher resolution features benefit from semantically strong lower res features, but the information propagation from lower level features to top level features is not optimal. Specifically, the lower level features can also be beneficial for larger object detection, at least in providing more accurate localization information. But in the current setup, the path from lower level to top level features is a very long one, consisting of a lot of layers. The authors then make changes in architecture for better information propagation from lower to topmost features. Specifically, they add a bottom-up pathway in addition to existing top-down pathway of FPN. This ensures that there is also another path from lower to topmost feature, which is a shorter one, enabling better propagation of features from lower to top levels, and thus helping us get better results. In YOLO v4, we use the same concept in NEC, that is, we move from FPN to Path Aggregation Network, but the implementation of connections are a bit different from original Path Aggregation paper. In bottom-up pathway, we take the higher res feature from lower level and first downsample it, then concat it with the same resolution feature from the top-down pathway, followed by a few convolution layers. The final prediction convolution layers in YOLO v4 operates on feature maps of this bottom-up pathway. The last bag of specials is a change in NMS. In NMS, to get rid of duplicate predictions, given a set of predictions, we get the highest scoring one and identify all the other predictions which have an overlap greater than a threshold with the highest scoring predictions. If the overlap is greater, then we only keep the higher confidence prediction and assume the lower confidence prediction to be a duplicate. But this also leads to false suppression of predictions, especially in cases of occlusion, where the overlap of two distinct objects could be high. The authors of Complete IOU Loss introduced DIOU NMS, which performs better than traditional NMS and reduces false suppression in such cases. Rather than just depending on overlap to identify if box BI is a duplicate of the highest scoring box M, we use IOU minus distance of center penalty term that was present in distance IOU loss. Just to remind ourselves, this penalty term is defined as a square of distance between center of boxes divided by the square of length of diagonal of the smallest box enclosing both boxes. This modification is with the assumption that boxes whose centers are far from each other most likely belong to distinct objects. So now even if two boxes have an overlap greater than threshold, but if their centers are far enough, we will not suppress the other box as a duplicate. This modified NMS was shown to give better performance than traditional NMS in the Complete IOU paper. Okay, so finally we have now covered all the aspects that the authors of YOLO v4 have mentioned in the paper, apart from these two. The scheduler part is self-explanatory, and the other just means that unlike YOLO v3, where we assigned each ground truth to only one anchor, in YOLO v4, multiple anchors are used per ground truth. Specifically in implementation, all anchors which have IOU greater than 0.2 with the ground truth are assigned to that ground truth. The authors of YOLOv4 do numerous experiments in order to test which settings are optimal. In this video, I only covered aspects which ultimately ended up being used in YOLOv4, but the paper mentions results on a lot of other features as well. So do take a look at the paper in case you are interested to cover every feature that the authors experimented with. In terms of performance, if we consider real-time detectors, YOLOv4 comes out to be the best one amongst those that the authors compare it with. Comparing specifically to YOLOv3, we get more than 10% absolute improvement from YOLOv3 variants which are in the real-time regime. And from SSD, it's even more, close to 20% improvement. In the final part of the video, we'll now look at the entire YOLOv4 architecture. In the official repo, you will find multiple configurations for YOLOv4. But for the architecture part of this video, we'll see all the components that are used in this YOLOv4.cfg config file. So let's get into it. We have already seen the different parts of the architecture at the beginning of the video. And the first one that we'll start with is going to be backbone, which is CSPDarknet53. And as we have seen before, this backbone is just going to be Darknet53 with CSP residual blocks. And instead of leaky ReLU activation, we now have Mish activation for the layers. We first have a 3x3 convolution layer, followed by a downsampling layer, which is again just a 3x3 convolution, but with stride 2, similar to YOLOv3, except now the activation is Mish. Then we have the first CSP residual block. Each CSP residual block has two 1x1 convolution layers with Mish activation. Both of these have the same number of filters, which is half the number of channels present in the input to the CSP block. One of these parts is passed to the series of residual blocks, each having 1x1 conv layer, followed by 3x3 conv layer and a residual connection. This entire residual block is repeated n times, where for the first CSP block, n equals 1. Then we have our transition 1x1 conv layer, followed with concatenation of this and the other part that did not go through residual blocks. This concatenated feature then goes through another 1x1 transition layer to produce the output of CSP residual block. If you recall, this is exactly what we had seen earlier in the video, when we were trying to understand cross-stage partial connections. All other instances of CSP residual block will be exactly same as this one, with only thing being different is the value of n, which basically indicates how many residual blocks are present. The output of the first CSP residual block then goes through a downsampling layer. After that, we have another CSP block with n equals 2 and then downsample. Then another with n equals 8 and downsample. And then the last two CSP residual blocks have n equals 8 and n equals 4. What we have up till now in terms of architecture is CSPDarknet53 backbone. Now we'll start with next specific layers, which are going to do feature aggregation for us. This backbone feature is first passed to a 1x1, 3x3 and another 1x1 convolution layer, but now the layers have leaky ReLU activation. In fact, that is going to be true for all the layers going forward. Mish activation is only used for backbone layers. Again, this is only for the model corresponding to YOLOv4.cfg. Few other configurations indeed use Mish activation for all layers, be it of backbone or detector. This feature is now passed to SPP to increase the receptive field. Like we saw, this involves a 5x5, 9x9 and 13x13 max pooling layers and concatenation of these together with input feature. The next part of NEC is the path aggregation network, and we'll first go through the top-down layers. After SPP, we have a bunch of convolution layers followed by 1x1 and upsampling layer. Up till now, our feature was of dimension size by 32, with size being the spatial dimension of input. After the upsampling, we now end up with size by 16 dimensional features. We concatenate this with similar size feature from earlier stage in the backbone, but only after passing that through a 1x1 convolution layer. The concatenated size by 16 dimensional feature again goes through few convolution layers, and after another 1x1 layer followed by upsample, it's again concatenated. This concatenated feature goes through 5 convolution layers to give our highest resolution feature, from which we'll make predictions for the smallest scale anchor boxes. Now we'll be going through the bottom-up pathway. We take this highest resolution feature, to which we added prediction layers, then downsample it to get size by 16 dimensional features. We concat this with the size by 16 dimensional feature from the top-down pathway. And again, after 5 convolution layers, we get our features from which we'll make predictions for the second scale of anchor boxes. For that, same as before, we have 2 convolution layers, specifically 3x3, followed by 1x1 prediction convolution layer. We repeat the same steps again. We take this feature, downsample it to get size by 32 dimensional feature, concat it with the same dimensional feature coming from top-down pathway, and again after 5 convolution layers, we have our prediction layers to give us predictions for anchor boxes of the largest scale. This completes our entire YOLOv4 architecture, with this particular portion being our path aggregation network, comprising of both top-down and bottom-up pathway. As mentioned earlier, the head is exactly same as YOLOv3, with predictions being done at 3 scales. So like YOLOv3, 9 anchor boxes are divided across 3 scales. The highest resolution feature caters to the smallest scale anchors, and the lowest resolution feature caters to the largest scale anchors. And the remaining scale is for medium-sized anchor boxes. So this architecture that we just looked at is based on YOLOv4.cfg, in which you will find Mosaic augmentation, Mish for backbone, SPP, PANet, grid sensitivity scaling, and complete IOU loss. But other features that we saw in the video, like Dropblock, cross mini batch normalization, attention module, DIOU NMS, is not used in this config. However, when you go through all the configurations, you will find some which indeed use SAM, DIOU NMS, and so on. And when you go through the code in the repo, you will find all the features that we have seen in the video implemented. Okay, so that's about everything that I wanted to cover about YOLOv4. Although I don't think I went through each and every detail of the paper, but I do feel that the video goes through at least the most important parts of YOLOv4. In case there are certain aspects which are unclear, do let me know in comments and I'll try to help you in whatever way I can to get a better understanding of it. In the next and final part of this 3-part video, we'll be covering YOLOv5. Thank you for watching this entire video right till the end, and take care.